Hello guys, I'm Pawel, and welcome to my first code-beam talk, Graceful Shutdown in Elixir, Try Not to Drop the Ball. Let me just switch to the pointer. I think we can almost skip this slide because you already kind of went over most of it. I'm gonna just slightly focus on the telnix part. So I now do Elixir at telnix, and we're at this next generation API first communications platform that provides carrier-grade services on our global private IP network that we have. And we use Elixir to build services, for instance, services behind voice APIs, so to allow our clients to programmatically control calls and conferences, and also for Fox APIs, and we are hiring. So going quickly back to our title slide, we're gonna talk about graceful shutdown and try not to drop the ball. And as we'll see, the ball has actually different shapes and different forms. And what we're gonna try to do is try our best to not be like Chandler here. Okay, so what's the plan? So we're gonna try to define the concept of graceful shutdown. And let me actually start the clock so I can time it. Graceful shutdown and discuss when it's useful. We'll go over how important, how to implement it in Elixir and OTP. All the examples will be in Elixir, but pretty much all the principles are for anything that will use OTP. And we'll illustrate this with a simple demo app that's going to be deployed to Kubernetes, where we'll step-by-step implement graceful shutdown for the most typical things, which is HTTP traffic, async tasks, and buffers. And those typical things, how we do it, this will actually allow you to implement it for more exotic problems that you have. Okay, so what is a graceful shutdown? So graceful or coordinated shutdown is when the application gets an external signal or notification to exit and is allowed to perform some cleanup actions. So this is in contrast to like a hard shutdown when the application just is immediately stopped. And then in the backend systems, this is very useful when we want to deploy new code multiple times a day without doing code reloading. So think like cloud orchestrators like Kubernetes. When we want to scale number of instances up or down manually or without a scaling, and this kind of is the same for if you're doing like resource-based auto-scaling or event-based auto-scaling or even time-based auto-scaling if you try to follow the sun with your users. And also when you want to perform maintenance activities on nodes running the service. So here, think like kernel updates. And you want to do all of this without affecting users or success rate of the system. And actually the recipe is very, very simple. So just 2 steps. A, don't take or accept new work. And B, with a sensible timeout, finish all in progress work and hand off any local state that you have. And during the talk, I'm going to try to make 3 key points. They're more about principles. So point number 1, test your graceful shutdown continuously in staging and in prod. Only this way you actually know that you're improving or degrading stuff. And if you already have, for instance, like a black box type end-to-end production test suite that runs all the time continuously and is testing your production with some synthetic traffic, you can use that. And for instance, when you're deploying, you can actually increase the traffic rate from this tester to see how your deployment perform when there's high load on the system. Can you actually do it, or can you have to go back to old school way? Oh, we have to deploy it, at night or off-peak hours. Point number 2, understand how you run and deploy your services. So this kind of mechanical sympathy to kind of the lower layer. In our example, this will be Kubernetes, helps a lot, right? Because we're not running just Elixir in a bubble, right? We're running this on some sort of infrastructure. And point number 3, that it's actually very, very easy to implement graceful shutdown in Elixir and OTP. I'm kind of new to Elixir. I've been doing Elixir for under 2 years now, and I did implement graceful shutdown in a couple of other technologies, and I like the Elixir way the most. It's very straightforward. Okay, so let's see all this in action with a demo app. So we're going to do a very a dead simple calculations API with a simple sum endpoint, which slowly adds the numbers. And by slowly means that I actually injected 100 millis sleep there just to pretend that it's meaningful work. So the input is going to be like like a list of numbers 1, 2, 3, 4, and the result is going to be 10. And I created the app about a week ago using the latest Elixir, the latest OTP, and the latest Phoenix. There's no HTML, no ECTA. And as we see, the application is called Calc. The top supervision tree is trivial, pretty much just telemetry and the endpoint. The router is equally simple. It only has a single route, some calling the controller. The Calc controller doesn't really do any validation because it's just a demo app. It just basically filters numbers if they're numbers and then passes everything to the Calc context. And the Calc is just taking the numbers, logging the numbers, then doing the sum using the slow math, and then logging the result and returning the result. And the slow math, as we expect, is just doing the sum, but it injects the sleep for 100 millis. Okay, and we're also going to go for a simple Kubernetes deployment. So I packaged the app with Elixir releases and a multi-stage Docker file. I created minimal Kubernetes deployment and service descriptors, which actually use a lot of defaults, and then deploy that to 3-node Kubernetes cluster on DigitalOcean. The app has 13 instances or replicas in Kubernetes lingo. And I'm using DigitalOcean load balancer that will terminate HTTPS and later will go for H2. And the load balancer is using keep alive, which means that it reuses connections between the load balancer and the nodes. And of course, the real deployment for something like this may actually be more complex or totally different, right? This is just an example. So you may have stuff like ingress controllers, edge routers, service meshes, or completely different deployment. The key point here is that we need to understand how those things run and how the deployment pipeline looks like to really take advantage of the graceful shutdown. Okay, so then I load tested the application from another VM using 500 virtual users, and every one of them is constantly doing new calculation for the same 1, 2, 3, 4 numbers, not reusing connections. So this is all, every time we're doing a TLS handshake, everything. And 500 users is actually not really, it should not really be considered a load. This is a very low load, but it already on a sample app like this can show how graceful shutdown, what role it plays. So here we see that when we just run it, that all of the, here we have the number of requests. So we had almost 76K requests. All of them returned 200K, and none of them was HTTP2, and that's how we want it, because we didn't configure the H2 on the load balancer, but all the requests are good. So now let's see how this behaves when we run the same load and deploy the application using the default rolling update deployment. And as we see, we had 13 errors. All of them were 503s. So it's just 13 out of 8.8K. So that's not really a lot, but we already lost the third 9 of our success rate. So let's try to do something about it. But before we do it, let's do another experiment. Let's actually see if the application can even scale up. We know that it doesn't do rolling update, but let's see if it scales up. We do another experiment, and here I just scale it up quickly from 3 to 13 nodes or pods in Kubernetes. And we also see that we have failures here, right? 8. And all of them 503. So this is the same error we're getting from a load balancer. So the reason why it breaks is when we scale up, Kubernetes creates new pods with our application and gives the traffic. But that means that our application is not ready to take traffic, because with the default, I made this mistake and I didn't tell Kubernetes when we're ready to accept HTTP traffic in this case. So the solution is very simple. We just create a health plug, put it above telemetry, because we don't want to have those logs. That's just pure noise. And the health plug just says, under health endpoint 200 status healthy. And then we define liveness probe and readiness probe. Readiness probe is the one that's actually used by Kubernetes Kubernetes to understand when it's okay to send HTTP traffic. So we use that new health endpoint. And I also explicitly define how we want to do the rolling update. In this case, I don't want defaults. I actually want to have 0 unavailable nodes. So we have 13 and the max search is 5. So that would go like 13 to 18 during the whole deployment. And then at the end, when the last 5 will be terminated, it will go back to 13. So let's see how that improves. We run a test and we see that the scaling test actually passes. There's no errors. Now Kubernetes creates the new instances and it will actually wait until the readiness probe passes, and then it will send the traffic. That means we're already ready because we had an HTTP endpoint for it, all good. So when we try to deploy, it actually passes again. And this may be interesting because we didn't do anything for the shutdown sequence, but it passes. So the reason why it passes is that if we look at the pod termination, after we did the rollout, we see that all 13 are still running and all 13 are still shutting down. That means that the seek term was completely ignored. So now let's stop for a second. Kubernetes, when it shuts down, it sends a seek term to a pod, or to all containers in the pod, and then it waits for, by default, 30 seconds for that pod to shut down. And if it doesn't, then it sends a seek kill. The 30 seconds is configurable. You can override it per your deployment. We didn't, so it actually killed after 30 seconds. And for a very dummy application like we have here, completely stateless, just returning, sum of numbers, that 30 seconds is already way more than we need to actually cleanly return all the responses. So actually, if your application is just, CRUD-like HTTP thingy, you don't really have to do it. Like the test proves that it's good enough. It's not the most optimal solution, but it works, it does the job. But let's say that for our app, we know we're gonna do more than just the CRUD app. So, but let's also answer why the seek term was ignored. So I made this mistake that in my Docker file, the last stage was just copying Elixir releases on the Alpine image, and was calling a bash script. And that bash script, and this bash script was supposed to run in the future, let's say some database migration or something like this, like calc release migrate, and then it runs the release application. And this is a pattern I saw a few times in a few applications. And the problem is that bash here will run the calc start, but it will not forward the OS signals. So here the Docker sees the bash as the process. It will give the seek term to bash, and bash will not pass it here. So we didn't even get to Elixir handling the shutdown. So we can even test it locally with Docker. If you just start that image, right, and we do docker stop calc, we see there's no seek term log, which we should see if we do it properly with Elixir. So there are two ways to fix it. One is just to use exec. Exec, old school approach. It will replace the current process with the new process. So this way, the calc will actually get the PID. We can test it locally. We see that the seek term is received. Or we can do it a more Kubernetes way. In this case, we can just call our application no shell script. It also works. And if we have to do any database migrations or any setup stuff, we should in Kubernetes actually use init containers or Kubernetes tasks. I'm not going to cover them because that's not the point, right? It's just if we understand the platform better, we know how to better use it. And we want to go for success. And actually, it doesn't look well. We still have errors. There are different errors now. Previously, we saw a lot of 503s. Now we see a bunch of end of files and one 502. So there's still a problem. However, here I want to make a note that if I would be giving this talk half a year ago, we would have way more errors. And most of them would be 502s. Now, the reason why this would happen half a year ago, because half a year ago, Phoenix 1.5 comes by default with plug cowboy drainer. So half a year ago, by default, I would be using Phoenix 1.4, which didn't have it by default. So 1.5 already has the cowboy drainer, which drains nicely all the HTTP connections at shutdown, internally calling range pool. And to simulate this behavior, like the 1.4 behavior in 1.5, you can just configure it with the drainer false. And there's also a way to pass all the custom options or parameters to the drainer itself in the latest Phoenix. So this was just a side note. Let's go back to fixing our V3, right? So let's take a look at the logs for a single pod. And we actually see that it is correctly draining connections. We see the seek term received, and we see that it's still doing, it shut down everything, and it finished. The problem is that there's a race condition between our app and Kubernetes. If we look at the timestamps here and here, the time it took to drain is about 300 milliseconds. And the actual sequence of shutdown in Kubernetes is that Kubernetes will mark the pod to be removed from the endpoints, and then it sends the seek term. And this marking means that the Kubernetes cluster asynchronously will kind of learn when it should not send the traffic for that particular service to that particular pod. And this 300 milliseconds is actually faster than the information propagation in the Kubernetes cluster, even though our cluster is like a baby cluster, right? This is just 3 nodes. So we have to basically give Kubernetes some time to remove the pod from the endpoints before we even receive the seek term. If we know that in some of the cases, our graceful shutdown can be that fast and can be faster than the Kubernetes internal messaging or knowledge propagation. So this is a tiny hook. It's called a pre-stop hook, and we just sleep for 5 seconds. So when we test it, we are back to all of them succeeded when we deploy. So this solves the HTTP 1.1 with TLS, and we solved it already having seek term processed by Elixir. And we can now modify the load balancer to do HTTP2, and HTTP2 test also passes. So we're good. So now let's actually complicate stuff. So let's try to implement async work using tasks. So let's say we want to log those calculations for some later on offline processing or something. It's not billing, but it's not also just like regular, text logs. And we want to do it async. And so we're going to send it every single calculation individually to InfluxDB, and InfluxDB is just a demo choice here. It doesn't really matter. And we're going to send it over HTTP after 5 seconds. So I added this 5-second sleep just to better show the effect of not having the graceful shutdown. If you don't have it, you may get sporadic errors, and it will be just worse for the demo. So what we do here is we publish async, we log that we're publishing, and we do the simplest possible thing, task.start publish. And then it is in the publish, we sleep 5 seconds, and then create the InfluxDB thing, and we send it over HTTP using Finch. But the important part is that we just use task.start. So at this point, because I know it's going to be more work, plus the cluster is using shared VMs, it was safe to bump the cluster to make sure we don't have any resource contention. So I bumped from the 3 to 7 nodes and lowered the deployment search to 3 seconds and slightly bumped the initial delay probes, especially that when I was doing on that day, DigitalOcean had some issues in Frankfurt data center. So when we do it, we actually see errors. So of course our HTTP traffic works because we did it before. However, we executed 3617 requests, but if we get the total number of events in Influx, it's almost 500 events less. So that's not good. So now let's talk about the actual Elixir stuff, how to do the graceful shutdown Elixir. So the seek term received by Elixir translates to system stop. Then the system stop actually stops all applications in the opposite order they were started. every single application stops in 3 steps. First, we run a prep stop callback on the application. Then it terminates the top level supervisor for that application, and then it calls the stop callback. And just to see it in action, right, we can just add some logs to this, right? So we have app starting, here we do the supervisor, we will do app started, and in the prep stop and stop, we will log app stopping and app stopped. And then we can try it locally with IEX. Sorry, and we see that we don't really see the app stopping and app stopped, because when you do it in IEX and you do Control-C, it doesn't really do graceful shutdown. It's not stopping nicely, the application basically kills it. So to simulate it in IEX, you have to do the system stop. When you do system stop, you will actually hit the app stopping and app stopped. So we have a local way to actually test this stuff. So now let's talk about supervisors. So supervisor starts its children in the order they are defined, which is top down, and then it terminates the children in the opposite order they were defined, which is bottom up. The starting sequence is that it calls function under start key in the child spec. Typically, that's a start link. And then the child process usually starts its work by executing the init function. Now, the shutdown sequence has a couple more steps. So first, the supervisor sends the child a shutdown exit signal. Then it awaits with a timeout for the child process to terminate. And that timeout is defined in the child spec. It defaults to 5 seconds for all the workers and to infinity for supervisors. And if the child process doesn't terminate in time, it sends a kill signal. That's the sequence. And now the child process. So if the child is not trapping exits, it will shut down immediately on the first shutdown exit signal. If the child is trapping exits, then the terminate callback is called. And now a note, exit signals are just messages to a process, and they wait in the same queue with other messages. They don't have a separate, right? It's not an immediate callback. And we're gonna see this in action in a bit. So how to implement graceful shutdown in Elixir? For most of the cases, just those four simple steps. So put all your important processes that you want to save under a supervision tree, statically or dynamically. Then define proper shutdown timeouts, which is basically do the timeout math, because you have to add all your timeouts through the different parts of the app, and they have to add up to the number that's still lower than, let's say, this Kubernetes overall timeout, right? So just to make sure that Kubernetes doesn't kill you after 30 seconds. If, for instance, your app for some reason usually needs 70 seconds, and you can configure it. So after doing the timeout math, you just, in those important processes, you trap exits and you implement the terminate callback. And that's the generic approach. So let's go for a very quick example. So let's add 2 gen servers, foo and bar, at the end of our application. They will be identical. So basically, they trap the exit and they implement the terminate callback that takes a reason in the last state of the gen server. And the foo is going to do, foo terminating with reason, sleep for 2 seconds, and say foo terminated. And bar implementation is identical, except that it doesn't sleep for 2 seconds, it sleeps for 7 seconds for the shutdown. So when we run it locally, we see that app starting, foo started, bar started, app started fully. Then we stop the application, bar terminating with reason, and then the next log we see is foo. So it terminated bar because it was the last, right? So it's going bottom up, and then it says foo terminating with reason. If you look at the timing, it's exactly 5 seconds later. 5 seconds is the default shutdown value for supervisor to kill the child. And we had a 7-second sleep in the terminate function for bar, so it was killed. It never finished the shutdown, but foo was able to normally terminate, and then the app stopped. So how can we fix the timeout for bar if we really know, for instance, that this one really needs 7 seconds? We can either define it, if we just use the gen server macro, we can define it as an argument here, and we can verify it if we run a child spec for foo. doesn't include any special shutdown value. The child script for bar will already have a shutdown value of 10 seconds. When we run it, we see that bar, in this case, terminated correctly. And then if we don't control the source code for some reason, we can easily override it. Well, first of all, the child spec is just a data structure, so we can do anything we want with it. However, supervisor child spec function already gives us possibility to do overrides, right? So here in the foo, which we didn't need any override, right? The child spec doesn't have it, and then we use the supervisor child spec func, and we're good. So let's go back to this note that exit signals are just messages. So in the foo, let's define the ping operation. Ping will just cast a ping message. Handling will be logging the ping and will sleep for a second. And then bar in the handle continue will send 100 pings to foo. And then on the right, we see the sequence. Let me move that window. We're stopping the app. Bar is terminating. Foo is still doing the work. Oops, sorry. Foo is still doing the work. Bar is fully terminated, but foo is still busy. And then we have the app stop. And if we look at this time, there was 33 and 38. Because for foo, we have the shutdown value of 5 seconds. So foo never even got to process that exit signal because it was busy processing the regular messages, and its queue was already big and it was slow here. And we can also see it even better if we, right after the bar terminates, if we get the last 5 messages out of foo queue, and we see that they were all like, foo was already processing like 23, 24, and its last message was 100, and then the exit signal. So this is important. Like if we have any bottlenecks in the system or very slow processing of something, we need to understand that with just the signaling, we won't be able to do the proper termination, and we have to rethink something. Okay, so now let's go back to our task issue. Let's solve it. We have all the knowledge now. So let's reproduce the problem locally, and it's very easy because the task, after it sent the message, it should log operation logged, and it didn't, right? Up stopping, and we just stopped. So let's first clean up quickly the supervision tree. So in the original one, I used the Finch. Finch is a HTTP client, but it's like an implementation detail of a log, right? So let's clean this up. Let's have just the calc log in the supervision tree. Let's now make the log a supervisor. So we will have that Finch that we just moved here, one level down, and we will add a task supervisor, which is a dynamic supervisor that will allow us to create tasks on demand, but they will still be part of the supervision tree. And then we will use tasks. So previously we were just doing task.start, but now we'll use the task supervisor.startChild, passing our supervisor that we defined in the subtree. And the function that will be run in that task process will first of all trap the exit, and then we'll run the function. And then we'll specify the shutdown value of 7 seconds, because that matches our 5 second, or it should be more than the 5 second sleep that we have in the publish operation. Now there's no terminate because task really doesn't have a life cycle. There's no messaging per se. It's just running your function in a different process. So when that function finishes, right, you're done, right? So there's no terminate callback, but it's important to actually trap the exit. So then it will send the exit and it will wait for that, like the supervisor will actually wait for that defined time, in this case 7 seconds, until it will actually kill the task if the task didn't exit before itself. And we tested locally, we see the operation is logged, and we tested on the cluster, and we see that this is the same number. All calculations are properly logged. So let's do one last change. Let's say we don't want to send to this influx every single operation individually. We want to send it in batches of either 500 operations or every 30 seconds. So in this case, we're going to change the log supervisor. We're not going to have the task supervisor here. We're just going to have the log server. And basically the publish async forwards the call to server, and the server will be doing the buffering, right? So it will have the publish size or publish interval, and publishing will be casting the message, and then the state would be the logs that we accumulate and the current timer. And then when we either are below the publish size, we just prepend the log. If we hit the publish size, we cancel the current, we publish the messages, cancel the current timer, and schedule another one. And then if we just hit the timer, we publish and schedule another timer. So very basic logic. And let's see how that behaves when deploying. And we see that this time the loss is even bigger, right? So we lost, yeah, almost 3K, you can say, of events. And the fix here is actually even simpler. So let's simulate this locally. It's also very easy. We don't see the log operations logged when it actually sent a full batch to Influx. And we just need to trap the exit in the server, in the init. And then in the terminate, we just send the last batch. So we know that the state has the last logs. So we're just going to publish it. And we test it locally that it actually logs correctly. And we test it on a cluster. And we're back to logging all the operations asynchronously without any issue. So now I want to go back to the key points, right? So again, it's important to test this stuff, and sometimes the test will show that you have to do something or that you don't have to do something, right? So we shouldn't be fixing problems that are they're not there. We should understand how we run and deploy services. Kubernetes here was just an example. I think it's kind of common or becoming common now, but there are many different ways to run our code, and we need to understand them to be able to have a very high success rates of the system. And that it's actually very easy to implement graceful shutdown in Elixir and OTP. Very straightforward. The supervision trees are an awesome concept. And yeah, that's all I had. So thank you very much. I will all the code that I showed here will be opened in a repo. I will probably push it in the next 10 to 15 minutes. It has all the scripts how to actually bootstrap clusters in DigitalOcean and do all those experiments if you want to. And here's a link to Telnik's career. So do check us out. All right, thank you.
Okay, thank you, Pawel. We have a couple of questions. Well, my first question is when you are developing something that is like a web server, what is your technique to stop receiving requests during the graceful shutdown?
So in this case, in the case of an example, right, this is a RESTful service, right? We were getting the request. The load balancer doesn't know about Kubernetes, but the load balancer talks to nodes. The nodes were Kubernetes nodes. So I was using the service abstraction from Kubernetes that with this 5-second sleep learned to not forward to those pods that were shutting down, right? And then the Elixir part, actually the out-of-the-box Phoenix part, was properly shutting down all in-progress requests that were handled by this box, right?
Okay. From the QA, we have a question here. During a deployment, let's say one of the workers is sending out an email communication. How would you maintain the state of the worker?
Mm-hmm. Okay, so also here, I think it's worth stressing that graceful shutdown, right? It's not it doesn't have anything to do with fault tolerance, right? This is for regular operations, right? This is like not dropping this kind of ball, right? So like we schedule those things, right? And we can handle. So if we already, for instance, for some of the use case have some persistence, right? And that state or the state is already shared between a couple of nodes in an Erlang cluster, right? And we know that this information already lives somewhere else, right? We don't have to replicate it, right? In terms of the emails, right? Depending on how long the email is the process, the email process will be sending, right? Or just the state. So you can either offload the state to an external data store or hand it over to a different process in a different node in your cluster. And then if you know that the operation, for instance, will be long, and if sending an email, let's say, even if it would be like 1 minute, that's not a problem. You can actually still do graceful shutdown for 1 minute, and you will define your graceful period in Kubernetes, for instance, to be 3 minutes. That's very okay, right? Your node will not get new work, but it will be able to finish those emails, right? But if you have longer jobs that last like half an hour and up, maybe it would be actually better to either, if possible, because it's a domain problem, either split it, or if not possible, use some special task management system to handle this. So Kubernetes, for instance, also has a task concept, right? Where we can spin a one-off tasks inside and the task itself is a container as well.
Another question, would it be possible to have a message in the process queue after the exit signal? Would that message be lost?
Yes, because, well, sending messages to process, right? We don't control the order from the different servers, right? Only the order from a single sender is preserved, right? So yes, there is a chance to get it, and there is a chance to lose it. So if you're just using costs, you will not get that acknowledged, right? So one option would be to use a call, because you're getting an ACK basically, right? You're getting a message back. And if you didn't get it, you may assume that it was lost either on the way to the process or back from the process.